Frog equals MA is a working model of a frog's legs that is meant to show students how a frog's tendons and muscles allow it to jump. In a real frog, the muscle contracts and applies a tensile force on the tendon. As the tendon returns to its original length, this propels the frog forwards. This falls under 3.3a of the Academic Standards for Science and Technology and Engineering Education, which includes describing how structures of living things help them function in unique ways. While teaching students about this natural science phenomenon, Frog equals MA will also teach students about the relationship between an applied force and the resulting acceleration, which would fall under Academic Standard 3.4c, identifying and explaining the principles of force in motion.
In review, the final product must be able to display the maximum acceleration of the frog legs after they are released. In addition, actuation of the brake pad, a change in the overall force on the legs, must produce a change in the maximum acceleration. The final version of Frog equals MA will be able to withstand drops of up to 4.5 feet, maintain original functionality after 10 weeks of storage, won't exert over 50 psi of pressure for safety concerns, and will ideally weigh under 5 pounds for easy transport. The product will be robust enough to function as intended for at least 250 demonstrations, and the acceleration readout must be within a 10% difference of the previous trials at the same force input. The time needed to repair any possible failed components will be no longer than 20 minutes.
The prototype includes wooden legs with a 1-inch diameter instead of metal legs with a 3/4 inch diameter. This change was made due to the amount of time it was taking to machine each leg member. The lever that compresses the legs has no locking mechanism, so the operator must hold it into place to prevent it from releasing. The force modulation lever setting is dictated by inserting nails attached to a wooden plate into drilled holes on the front of the base. The force modulation lever is pushed downwards and the plate is pegged into place. This lever is then released and stopped at a certain position depending on where the plate was placed. The legs are attached to a guide bar by a simple collar with pegs that go through the femurs.
The first experiment was conducted to evaluate the Young's moduli of the two different elastic bands that were purchased. Various masses were attached to the end of each elastic, and the resulting change in length was recorded. The stress and strain were calculated, and Young's modulus was found from the slope of the linear trend line. Although both options have the same Young's modulus, the orange elastic band was chosen because its larger cross-section allowed for larger force with the same degree of elongation as the pink elastic band. Based on this information, with the band stretched to 9.5 centimeters from an original 8 centimeter length, we should be able to get a force of up to 18 newtons. The other experiment was carried out to evaluate the performance of the braking system. A number of trials were performed for different forces. The first set of trials involves releasing the left lever with no friction applied by the force modulation lever. The second set of trials was run with the force modulation lever at the lowest friction setting. Averages for the acceleration in each set of trials were calculated, and as intended, adding friction to the force resulting from the elastic tendons did decrease the average acceleration of the legs. The only problem was that the other force modulation lever settings created more friction than the elastic bands were able to overcome.
In order to have a prototype created in the allotted time, manufacturing the entire biomechanical structure out of metal was not feasible. Using wood reduced friction in the joints, reduced accuracy in the manufacturing tolerances, thus decreasing accuracy and the force variability. With this prototype, we were able to demonstrate the mechanical motion of the frog leg, as well as the applied force in measuring the acceleration output. For the final device, the leg bone segments will be made out of a durable plastic. This will cut down on the friction in the joints, as well as the manufacturing time, as they can be cast in a mold repetitively for production quantity. The elastic bands will also need to be changed to ones that allow for more elongation and a higher spring force. This will allow them to be able to overcome the full range of motion of the joints as well as of the friction force settings. The fully realized version of Frog equals MA will have the femur, tibia, and tarsus bones constructed out of cast plastic for decreased manufacturing time and decreased friction in the joint. The left lever used to compress the legs downwards will be connected to a ratcheting mechanism so that there is no risk of an accidental release. A button will be pressed to disengage the ratcheting system, allowing the elastic bands to extend the legs. The front face of the base will have incremental slots to lock the force modulation lever, allowing for quick and easy manipulation. As the force modulation lever on the right is set to lower positions, the bicycle brake pad will be actuated to apply friction to the cable used to compress the legs. This will vary the force applied to the legs, changing the acceleration. There will be a frame that connects the legs to the guide bar, and it will be large enough to accommodate a plastic frog that will move with the legs. The acceleration of the legs will be recorded by an accelerometer and displayed so that the user can see the impact of changing the overall force and what it does to the acceleration.